of J. That is, H is 1 to 1. My definition of saying this subset is contained in that one is that some function has this composite equal to that. Now I claim if this happens, that function has to be 1 to 1. That means if this subset is contained in that, this thing is actually a part of J. Nothing is mashed together. I want to show that in this case, H has to be 1 to 1. So that's a converse of what I just proved. We proved if F from A to B and G from B to C harmonic are 1 to 1. Then so is GF. We gave that proof. But now I'm going to show something more. Theorem. Which one do I want here first? If G from B to C is 1 to 1, and so is GF from A to C, then F is 1 to 1. That's the situation over here. Well, to adjust the notation, if J from J to A is 1 to 1, and so is I, which equals J I, which equals JH, then H is 1 to 1. So I've got this is 1 to 1, that's 1 to 1, this composite equals that. I would now like to know, look, I'm saying this subset is contained in that. I'd like to know this is a subset of that thing. I'd like to know that this arrow is 1 to 1. So the situation we've got is, well, I'll draw it over here. What I'm kind of running out of marker on this one. Yeah, I got it there. Yeah. Let's look at X and Y here. I guess I'm afraid I'm going to have to erase this. So I know that J and I, which equals JH, are 1 to 1. I want to prove H is 1 to 1. So, to do that, assume Hx equals Hy. See, that's the relevant assumption. I'm trying to show this is 1 to 1. So assume it has the same composite with both of those. Now I want to show those had to be equal. And I'll be done then. If I show that this assumption implies those are equal, I'll be done. And then JH of X has to be equal to JH of Y, because you're applying a function to the same thing on both sides. And JH is monic. So X equals Y, which is what I needed to show. So now what I know is, if one monic factors through another, the factoring arrow is also monic. Or in terms of subsets, if this subset is contained in that, it's contained as a subset of it, which you would like to be true, and it is true.
Then, excuse me, it back to the result, the theorem you want to prove.
This one.
I factors through J.
Yeah.
What's the original meaning of this?
This just means there's some function so that composite equals that one. Yeah.
And then you come from.
Well, yeah, no, I sketched the proof of this here, but this, we need to use characteristic functions, and we need to use the existence of intersections, so there's a little more going on there. It's a longer proof than this one. So, now then, an equalizer is a function that, so that composite is the same as that composite, and such that whenever I have a function where that composite is the same as that one, that function factors through here. What does that mean? It's not really transparent what that means. First, let me show. Well, I'll write in words. Every equalizer is a subset. Or in general category theory, because it's not just every equalizer is monic. That's our general term for one-to-one. Every equalizer is a subset. I told you, think of this as the subset of A that contains the solution, the things that where f of x equals g of x. Well, let's at least show that it is a subset. How do I know that an equalizer is one-to-one? All right, over here. Yeah. So, assume that E, mapped over by E to A, F, G, is an equalizer. Right, and now I want to show it's monic. So what I need to know is, so I want to show for every x and y elements of E, that is, whenever I have x and y that are elements of E, if EX equals EY, if they have the same composite, then X equals Y. Then they were equal to begin with. To say they have the same composite means there's the same arrow here. EX is the same as EY. Certainly I can compose both E and X with, I can compose both X and Y with E, but my assumption is they have the same composite. So now I've got some arrow here that factors through x and also y. But remember the definition said a unique u. The definition said this can only work for one function here. So x and y had to be equal. So equalizers are subsets, really directly from the definition, from the uniqueness clause of the definition. So now we've got that an equalizer is a subset. Now I want to prove an equalizer well, an equalizer for FG is an isomorphism if and only if F is G. I claim that this equalizer is an isomorphism if and only if those were equal to begin with. So, two steps. First, suppose, well, here, we'll assume this is an equalizer. Suppose F does equal G. Suppose F equal G. What is the equalizer of a function with itself? Well, in that case, the identity function on A makes the composites equal. I'll just rewrite this as F. The identity function composed with F is F. And so, the identity function has to factor through here. So, it factors by U. So, EU is certainly the identity on A. That's the definition of equalizer. How do I know that UE is, how do I know, yes. So, let's see. U followed by E. U followed by E. Well, that's E. The identity arrow goes both directions. Right. Oh, yes. So UE. E followed by U is, oh, yeah. So, U followed by E followed by U. Yeah, so now I want to show that E followed by U is the identity on E. Right. But it's good enough to show, since we now know E is monic, it suffices to show that E in front of UE equals E in front of 1 sub E. Because the nature of monics is you can cancel them on this side. And we know that every equalizer is monic. But this we know is equal to EU followed by E, which we know is equal to E, which we know is equal to that. I want to show that this composite is the identity on E. But this arrow is monic, so it's good enough to show that that composite is the same as the identity composed with that arrow. But those are both obviously equal to E, so they are equal. That's one proof. A more sophisticated proof is actually a better one. To show that the equalizer of an arrow with itself is an isomorphism, it's good enough to show that this diagram is an equalizer. Because we know that equalizers are unique up to isomorphism, so if this diagram is an equalizer, then F and F, rather. If this diagram is an equalizer, then every equalizer for that is equivalent to this, so it will be an isomorphism also. How do we know this is an isomorphism? Well, this is directly by definition. The equalizer, that's directly by definition. I need to show that every function f that has the same composite with those factors uniquely through here. That's the definition of equalizer. Well, every function h has the same composite with those because those are the same function. So I now need to know that every function factors uniquely through here. And of course it does. It factors as itself through there. Yeah. So there's a proof that the equalizer of any function with itself is an isomorphism. Because the identity function is certainly an equalizer of a function with itself, and any two equalizers are equivalent. So equalizer identity, but the more interesting result, the harder result, second, well, it's not much harder. If this is an equalizer and E is an isomorphism, then F equal to G. Anytime an equalizer is not, so we know the equalizer of a function with itself is an isomorphism. Up to equivalence is the identity. Now we want to know conversely, suppose this equalizer is an isomorphism, then those those functions were equal. But that's also easy. Actually, it's also easy. What does it mean to say that E is an isomorphism? That means then there is H from A to E with do E first and then H, that's equal to the identity on E, and do H first and then E, that's the identity on A. That's what it means to say it's an isomorphism. If E is an equalizer, for F and G, then FE equals GE. That's part of the definition of an equalizer. Together, but then if both happen, then F, which is certainly equal to F followed by E followed by H, because this is the identity, that's equal to F followed, F after E after H, the associative axiom. That's equal to G following E, H, by this assumption, which is G, E, H, which is just G. So the equalizer is an isomorphism if and only if those arrows were equal. And that result in subobjects depended on. Okay, so let's prove the result on subobjects. Well, here's an earlier one. Every subset I of A is included in the identity subset. Anytime I have a subset of A, I, well, there's the identity function. We didn't. This function is clearly one-to-one. If take any x and y, if x and y have the same composite widths, they're equal, because of course they are each their own composite with this. So this is a one-to-one function. I want to show that for every subset of A factors through here. What it factors through the only way it could, it factors through by itself. Yes. So every subset is a subset of the maximal one. That makes sense. This is a subset that's all of A. Of course, every element of A factors through this. It's the same proof. I claim every element X of A factors through here. Well, sure it does. The only way it could. So this is a subset that contains every element of A, and every subset of A is a subset of it. What is the characteristic function? Of 1 sub A as a subset of A. So that's this subset of A, 1 sub A as a subset of A. Remember, every subset is an equalizer of its characteristic function, whatever that is, with the composite, take A to 1 and then go into to true. So this is the composite true sub A. This composite is a constant function. Whatever element you had of A, you take it to the sole element of 1 and you take it to the element true. This is a constant function that takes everything in A to true. And our axiom said every subset is the equalizer of that constant function with its characteristic function. What is this characteristic function when this is the whole thing? The only way this can be an equalizer is if the characteristic function, we just proved this, equals true sub A. That's the result we just proved. The characteristic function of the whole of A is the constant function true. That makes sense, right? I mean, the whole of A is the thing that its characteristic function takes everything to true. What else could I show on this level that I hope might help people to get used to thinking this way? Yeah. Let's look at, let's look, the equalizer. Which elements, let's say, so given A, F to B, and G to B, and we'll suppose we're given an equalizer, so E is an equalizer of that. Which elements of A have X element of E? What are the elements of that equalizer? That is, which arrows here are elements of the equalizer? Well, let's see. So, 1. If X is an element of E, then f of x equals f of g. I claim that all the elements make those two equal. Why is that? Because x element of E means there's some h with E after h equal to x. That's what x as an element of E means. It means x factors through there. So, f of x equals f of EH. But that's f of E followed by h. Yes, but FE equals GE. That's the definition of equalizer. F of E had to equal G of E. Now you don't have the definition of equalizer up here, but get it back up. Part of the definition was that FE equals GE. So FE equals GE, so FE followed by H equals GE followed by H, which equals G followed by HE, which is G of x. So certainly, if it's an element, then f and g take it to the same thing. Conversely, if fx equals gx, if this composite equals that composite, the definition says there exists an H. That's the definition of equalizer. Which means X is an element of E. It's just spelling out the definitions, but you're not used to the definitions yet. It takes, yeah, I have to think about them because I don't spend most of my time with dentists. You know? Yeah.
Could you say, could you keep sort of correspondence concept in set theory of equalizer? So it's just, of course,
Well, I mean, we could give this definition in Zermelo-Frankel.
how do we think it in set theory?
Well,
As a little.
In Zermelo-Frankel, you wouldn't give this definition. In Zermelo-Frankel, you would say, okay, this is good, yes, I like this. In those days, I have to follow up with something you said the day before. Today, I get to. In ZFC, we would say, the closest we come to this is, given F and G, both functions from F to B, define the subset of all x in A such that f of x equals g of x. We would just say consider that subset, that specific subset. Now what we're doing here is we're defining this up to isomorphism. We're saying we can't pick out a specific subset. All this stuff is done up to isomorphism. So what's the isomorphism invariant property this has? This has the isomorphism invariant property is, now in ZFC, the element x isn't really a function to A, but it determines a function to A, right? And for every element x, there's certainly a function from any singleton to A. We're saying this thing factors through here if and only if f of x equals f of g. And if we were trying to pin down the exact elements of sets, if we were doing a fine-grained analysis of our set theory, suppose we're doing descriptive set theory, and we're really concerned with keeping track of all the details of the construction of a set, so that we really want to know how the set was built, we would do it this way, not this way. But the truth is that in most mathematics, people don't want that kind of fine-grained analysis. The tools of ZFC developed over decades for very skillful work. I am not saying, I don't know if anybody thinks I've ever said this, but I'm sure some people, I am not saying ZFC was a mistake and people shouldn't have done it. I'm not saying ZFC is a bad thing to use for what it's designed for. It's an excellent thing to use for what it's designed for, which is currently investigation of large cardinals. Before that, it was investigating the axiom of choice through the notion of constructability and then eventually forcing. It's fine, it's good for that. But most of math isn't much like that. And that's why a textbook like Lang's Algebra or Munkers Topology doesn't really talk this way. They'll use this notation. I will use this notation as a selected equalizer. Remember, I've already said I'm going to use this notation to mean a selected product for A and B. I'll write this way for a selected product. But it has no different properties from any other product. I will use this notation for an equalizer, a selected equalizer. But all I know about this thing is it has that property. This is not, it's a fine notation, but on my foundation it's not understood the way it is in ZFC. ZFC is fine for what it does, but the truth is that most math students never get the idea of iterative membership. They certainly don't, they never hear of the well-founding axiom. They never hear what is a first order formula with one free variable. They don't know the basic concepts needed to give the axioms of even Zermelo set theory, let alone Zermelo-Frankel set theory. There's a real cost. If you want to teach students even just the axiom scheme of separation, most math students don't know an axiom scheme from an axiom. Zermelo set theory does not have a finite number of axioms. It's often listed with a finite number, but the last one isn't a single axiom. It says, take any formula in the language of set theory with a single free variable. Then write this formula that uses it. Then there is, it's an infinite scheme, it's an axiom scheme. Axiom schemes are lovely. Some extensions of ETCS use axiom schemes. But this doesn't, and most math students do not know the difference between an axiom scheme and an axiom. So in that sense, they cannot understand what the axioms in ZF are. But yeah, so if we were doing it in ZFC, we'd pen this down, we'd say it's this subset. But what's the crucial property of this subset? That the elements are precisely, well, it says here, the elements are the things that make it equal. I'm saying, instead of up to isomorphism, I'm saying an element factors through here if and only if it makes them equal. Now, are there other things here that we could revisit, usefully revisit? Okay, so this subset is the whole of A, just in case that's the same function as that one. The whole of A, the characteristic function, takes everything to true. It follows, but not from the axioms I've given so far, that there is another element over here, and there's a constant function that takes everything here to that other element. That's the characteristic function of the empty subset of A. Actually, it doesn't follow from the axioms I've given you so far that there are any empty sets. It does follow from the axioms as a whole, but not from the axioms that we've discussed so far. And there's another difference I'll mention. In ETCS, an empty set is an initial object. That is, for every set A, there is a unique function from the empty set to A. But in ETCS, this only defines the empty set up to isomorphism. We do not prove there's only one empty set. In ZFC, of course, there's only one empty set because the set is determined by its elements. If it's got none, it's the only one that's got none. But for us, empty sets are only unique up to isomorphism. Empty subobjects of a set are determined up to equivalence. They're all equivalent. So, and they are the smallest subset. The empty subset factors through every subset. The same as every subset factors through the maximal subset. So there is a unique empty subset of A up to equivalence. There's a unique empty set up to isomorphism. But there is not a simply unique empty set here. Whereas in ZFC, of course, there's a simply unique empty set. Yeah. Definition of addition. Well, I mean, I have sort of sketched this. Well, I did sketch it. To define the addition function, well, by defining its transpose, which goes from n to the function set. Right, that's how we always define well, okay, there's lots of ways to define a binary function, but one of our favorites is use of transposition. Define its transpose, and this is one case where that works. How do we always define a function from here? That's by defining the value at 0 and define the value at successor of n in turn as a function of so this is the plus 0 function. We have to define the plus 0 function. This is the plus n plus 1 function. We have to define that in terms of the plus n function. That's how our set theory works. Well, the plus 0 function, this is it's the identity function. But I will admit there's a little complication here as an element of the function set. Right. This is supposed to be an element of the function set. So I have to define the plus 0, the identity function, as an element of the function set. So, for the first time I'll go over and use this. What's the identity function as an element? Well, for any A. I'm not going to, for one thing, I'm not good at writing that bold-faced letter. I'm going to do, what's the identity? Well, call it transpose of the identity on A, which is a function from 1 to A to the A. Right? I'm going to give it this name, which will turn out to be a good name. Yeah, so my goal is I want to know which element of this is the identity function, represents the identity function. Well, its transpose is technically a function from 1 cross A to A. Right, because any arrow to an exponential is determined by its transpose. The transpose I want is the one that projects this onto A and then follows it with the identity. So it's nearly the identity on A. The transpose is almost the identity on A, except there's this minor detail that this product isn't exactly A. But I can project it onto A and then compose with the identity. So here, I just need to say what element I want here. Well, I take the identity function on 1, take the product with the singleton set 1, take its transpose, that's this. And the add n plus 1 function, I don't know exactly how to express that here. Well, we're doing this inductively, so we get to suppose that we knew what the add n function was.
You have to define what's 1 and what's n.
Yeah. Now I need to, so now I want the function here that takes a function f from n to n and turns it into f plus 1. So by induction, I'm allowed to assume I have this. Now I'll get this. The trick is I need to know this. This is my transition function. Over here, okay, so I've done that part. And once I do this part, I've done all of it. So what remains is to do this part. I need a function, what was my name for it? F, yeah. That takes any h element of n to the n, which intuitively is just a function from n to n. This isn't precise, but I'm motivating it. And gives h followed by s from n to n. Right, that's what I need down here. I need to put down here, I need to take a function from n to n and take it to the composite of that function with s. Given. So it's actually, I'm going to do a more general problem. Given, well, I'll call this function s also. Yeah, this goes from any a, let's see. No, I'm going to have this go from b. This goes from any set b to c. Define the compose with s function as a function from b to the a to c to the a. I want to be able to take any function from a to b and compose it with this. That's a little hard to read. Everything I write is a little hard to read, I'm sorry, but see, I want a special case of it. But the general case is actually going to be easier to make out because we don't have the same letters and we don't have so many letters. I want to know, what is the compose with S function? It takes any function from A to B and returns that function composed with S, which is now a function from A to C. How do I define a function to an exponential? Well, in principle I might do it any number of ways, but the basic way is define its transpose. B to the A cross A to C. And the answer is, I guess the answer will make more sense after I give it than trying. The answer is, take B to the A, cross A, evaluate to A. Remember, we're given this evaluation function. Evaluate to B, rather. Evaluate, that goes to B, right? Evaluation takes a function from A to B and a value in A, gives you a value in B. Compose it with S.
Yes.
This transpose should take a function and an argument, evaluate the function at the argument, and then apply the function S. So that's what I do over here. F transpose. Well, F transpose equals, take n to the n, cross n, evaluate, that gets us to n, and now take the successor function to n. This function is the transpose of that function. And I take this function as my f down here because this is now n to the n on both sides. For f, I take the transpose of this function because the transpose of this function takes any function from n to n and returns the function that applies that and then composes the successor. So now I've given I've defined it in Peano's terms. I've said, what's x plus 0? Well, that's the plus 0 function applied to x, which is the identity. And what's x plus successor of n? Well, that's the successor of that successor applied to the x plus n function. It's the same point. It's just this using this specific formalism.
Sorry, I forgot the evaluation thing.
Yeah.
So
Oh, I guess I did function sets after. Did I do function sets after? No. I must have done function sets before. Oh, right. This was a discussion. Yeah, the function set. Remember, our definition of the function set is it's not just this set, it's the set with the evaluation function. Let's reverse the evaluation function. Oh, we're past time to break. We had 2 breaks.
yes.
Okay, good. So we're in good time. Yes, we have to. Yes. Yeah, the idea here is given G from C to B to the A, what is evaluation, and I didn't put subscripts on that, of G cross 1 sub A? Well, what is well, yeah, let's do it intuitively. What is this thing applied to a given pair, GCA? Well, it's evaluation applied to G of C together with A. I'm redrawing the parentheses. I'm grouping it this way. This is G of C together with A. And what's the evaluation of G of C at A? Well, G of C is a function from B to the A. The intuition is this evaluates that function. This is G of C applied to A. Now, officially, this is just a notation for that. Yeah. So, okay, arithmetized analysis. I have not proved it, but these axioms imply the existence of, we can define things by equivalence classes. We can normally arithmetized analysis, we talk about arithmetized analysis. Begin with the natural numbers. Define the integers as a, well, set of equivalence classes on n cross n, where the pair AB is equivalent to CD if and only if A plus D equals B plus C. People are familiar with this construction. The idea is we start with our set of natural numbers. We know what addition is on the natural numbers. We can take pairs of natural numbers. We can define this equivalence relation using just addition. So intuitively, the pair AB represents A minus B. We can't, in general, subtract one number from another. But we can take this equivalence relation, we can take equivalence classes for it, This is not the only way to construct the integers out of the natural numbers, but it's one way. So, in particular, A0 represents A plus A as an element of the natural numbers, and 0A represents minus A, an element of Z that's not an element of the natural numbers. Yeah. Now, in fact, this set theory does let us form the set of equivalence classes for any equivalence relation. So we can do that. We can define Z as a set of equivalence classes there. Then, okay, are people, I don't know if there's any questions about that, or, but.
There's something a little bit error here. Like, see, according to previous definitions, 0, 1, and the 1, 0 should be the same equivalent class, right? But 0, 1 should be minus 1. Anyway, it can be.
Yeah, let's see.
Can be.
I must have said something, yeah. Okay, so what we want is, we want A minus B to equal C minus D. So that's A plus D. So that's A plus D is B plus C. Right, no. So 1, 0, if that was to, is that equivalent to
0, 1.
0, 1? Well, that's if and only if 1 plus 1 equals 0 plus 0, which is, yeah, so it does, because we're crossing the places of the terms. So yeah, so this is not equivalent to that. Yeah. Yeah. I thought I had it, but I can make mistakes, yeah. So the point is, we'd like to say this, but we can't because we don't have subtraction yet. So we say this instead, because this we have the terminology to say, and it's equivalent to that. Let's define Q as a set of equivalence classes on Z cross N where the idea is a pair AB will represent A over a successor of B. So our denominators have to be non-zero natural numbers. Our numerators can be anything. So we want to get all fractions. So what we say is AB is equivalent to CD if and only if successor of D times A equals successor of B times C. A over successor B is equal to C over successor D, just in case this cross multiplication works. So we define the rationals that way. This is standard stuff in Zermelo or Frankel, in any book that goes through trouble to construct these things. We can do that here, but you know, in the textbooks, in ordinary textbooks, after they've defined an integer as a set of equivalence classes of pairs of naturals, they then proceed to act as if the natural numbers are integers. The natural numbers are the positive integers. Edmund Landau wrote a nice book on analysis where he did this. And this is in the 1930s. And what he does, he describes the integers by the Peano axioms, he describes the naturals by the Peano axioms, he describes the integers this way, and then he says, I'm now going to change my definition of natural number. From now on, a natural number is an integer which is equivalent to one of this form. And then he uses the integers to define the rationals, and then he says, I'm now going to change my definition of integer so that an integer is a rational number that's equivalent to one of this form. Because remember, the denominator is a successor of the thing that came here. Then he defines the reals as Cauchy sequences on the rationals. He says, I'm now going to change my definition of rational to mean one that's a real number that's equivalent to one of the form a constant Cauchy sequence. So if we do this, did I make it? I think I made a slide for this. Yes. And it's not just here. Yeah, I made a slide talking about complex numbers. Elementary textbooks typically define complex numbers. We say a complex number is a pair. There's two main definitions of complex numbers in textbooks. I went and looked.